Okay, so we're going to continue now. We have discussed some basics and fundamentals of the radiation transport equation, yeah, and arrived at the standard equation for one-dimensional plane parallel systems. So we can see that this again is a linear ODE now with a fixed optical depth scale along the z-axis as discussed. And of course we can solve this then with the same sort of technique as we did the last time for the homogeneous slab. Only here we have to apply a different integrating factor. Hopefully it should be intuitive. Previously we had tau nu, right? That was along the ray. So now we have tau nu zeta, but we have to divide it by mu. We also have to put a minus sign because we have switched the signs on that because of the axis directions. Okay. And if we apply this, we can solve it. Yeah. But we did it already for the homogeneous slab. So now I'm not going to do it again. Now I'm just going to write down the solution and we're going to discuss what that solution means. I'm going to try to interpret it a little bit to that. You know, you can do the solution. It involves a little bit of algebra. It's actually an exercise in the booklet, and there's even for a solution for you provided in by the TAs in the corresponding booklet for that, right? So it is there. I'm going to write down what we now call the formal solution of this equation, which is now I nu of tau nu 1 in the z direction. It's a function of mu equals to I nu tau nu 2 in the z direction. It's a function of mu plus e to the minus tau nu 2 minus tau nu 1 z direction, where this is of course tilted with the mu, divided by the mu. Then we have to add the source function part to this. And we have not assumed now that this source function is constant as we did for the homogeneous slab. So then we're going to have to keep it inside the integral. I'm going to put it as t nu e to the minus t minus tau nu to c divided by mu d t nu divided by mu. So this is a very nice expression. It looks cumbersome. Let's see if we can interpret it a little bit, huh? Here we have it. So first, formal solution. That is because the work is actually not done. We've just written down the solution, but we haven't solved the integral, right? Now, it is only in special cases, like previously in the homogeneous slab, we assumed that this source function here was constant. So then we could just plug it out, and then we can solve it directly, right? There are other instances, like the one we're going to discuss later in a few minutes, where we can assume some sort of dependence, and then also solve it analytically. Now, today, most of practical research applications as well, they solve it numerically. So then you have to obtain your expressions for the source functions from your medium, expressions for your optical depth scale, and then solve this equation numerically with some sort of technique. Now, what does this equation mean? Well, first, let's see, we have the media here, right, with our plane parallel layers, and say we have some sort of intensity I nu there of tau nu 2 and along some angle mu, right, where mu is defined by this theta angle here. And then we have another position there, up there, which then is I nu 1 and mu. Okay, so then imagine here was our source in this case, if we make the analogy to what we had before. And then we're interested in how does the specific intensity along the ray here change as we come up here. Okay, that's essentially what it says. We have this solution here, which is this incoming, or the emergence, and then this is modified by this. And the first term here is familiar to us from our previous class, from our previous lecture. It's just this exponential attenuation law of the source, the extinction, the absorption part, right? Now here you see that this is just governed then by the difference in delta tau nu theta. That's this. But then it's tilted by mu because, of course, the path length is a little bit longer here. Yeah? So that's just that part. And then it's exponentially attenuated. And then we have the source. And that source function now, yeah, where t here is just an integration dummy variable. It's just to not confuse it with all the taus that we have moving around, right? Now, the source here is not just from the background or anything. The source here now, technically, is added at each of these small points along the ray until we reach the final position. Okay? Now, if you add some beam here, a source, then of course that has to also travel all the way up there. This one is added there, it has to travel all the way up there, etc., etc. So there is your source, but then that source is attenuated with the light that is the difference between the I nu 2 and the actual position. Okay? So from that until the position where we want to integrate to. Okay? And then, of course, again, we have the tilt in mu, and we have the tilt in that. So that then, when you sum this all up, it becomes an integral. You know, integrals in this context are just sums. You sum up all the contributions, they're all exponentially attenuated, and then you get the final answer up here, which then involves solving this integral. So that's essentially what the radiated transfer equation and the transport of light there means. Now, let's look at this for some special, hopefully interesting, at least they should be somewhat relevant examples. Now, let's say that we are up here, very far away. Our plane parallel atmosphere here, all right. And t-axis somewhere around there. And then the tau nu c-axis going in this direction here. Now, at the surface, at the end of the object, we have free streaming in vacuum until the light reaches us, very, very far away. So here, tau nu of c, can set this to 0, all right? Now, this object is very, very thick. It's optically thick in this case. Think about a star or an optically thick accretion disk or something like that. So down here, when we move, then actually tau nu of c, we can take it as going to infinity. This is called the semi-infinite medium or atmosphere, since that is where it is classically derived from for in the context. Now, we are then interested in obtaining the intensity here at an optical depth 0 and at the angles mu. And that we call then the emergent intensity. We could also, and that's technically what one needs to do when one, for example, do models of these type of systems, we could be interested in the radiation field inside the object as well, okay? But now we're interested in what actually is the emergent. That is that the radiation escaping from the atmosphere, for example, in the direction to us. Yeah? That's what we will observe in the absence of these type of interstellar or intergalactic extinctions that we talked about last time. So, all right. We put this in, then I nu of 0 mu, then we can see that, well, the first here term is actually going to be 0, because this one is 0, but this one is goes to infinity in the semi-infinite case. So we're not going to get any contribution from here. So the only thing that we're going to get is this one over there. Yeah? And we have said that this one is 0. So we're going to see this from 0 to infinity as nu of t nu e to the minus t nu divided by mu d t nu o. Pardon for that. Okay. So now we have a neat equation for the light that emerges from this plane parallel semi-infinite atmosphere. I'm going to write it again up here. So we can take away the stuff over here. Right. So what did we want to do with this now? Well, that's a good question. Let's look at some examples, okay? First, like we had before, let's assume now that S nu of T nu is actually just S nu, a constant, okay? Right? Well, then this is not such a difficult integral, hopefully. We could do a variable substitution and show it with x, t nu minus mu, etc., etc. We evaluate this, then I nu of 0, mu, is just going to be the source function, right? And that we could have that we should have known already, because that was the result we obtained from the homogeneous slab in an optically thick media, right? So the homogeneous slab would be the mu equals to 1 case here, and in this case, tau nu would be much, much greater than 1. And then we get that the specific density is just the source function, right? So that checks out. Very nice. Now, you can do this as a little exercise for yourself to verify that if you have this and it is this, then the flux in the c direction should be pi times the source function. Yeah? You can verify that, get you working with the expressions for the flux, right? And then you compare that to when we had that, okay, before we had started to do the radiative transfer, we had that the flux from this type is like pi times I nu. In the case that we had no incoming radiation and the radiation field was independent. That's a little bit of a next exercise for you. Now, we're going to do another example, because the drawback with the homogeneous slab is, of course, that, well, a lot of objects aren't really homogeneous in that sense, right? The source function do vary with position. So we're going to assume now that it varies as a function of optical depth. And it varies linearly as with the optical depth. It increases with the optical depth, which for our semi-infinite atmosphere means that the source function increases as we move into the material. Okay? Again, a star is the natural example to think about here. Because we know from our other courses that the temperature increases inward, so we can think, well, the source is roughly the Planck function, and so the Planck function should be bigger and bigger and stuff like that, okay? One can do this more quantitatively, but that's a qualitative way to think about it in this way. So if we assume that now, and we plug that into this, we get I nu 0 mu equals 0 to infinity A nu plus B nu T nu, yeah? It's the source now, using the dumb integration variable, dt nu mu. Okay, so the first term here, we recognize, that's just the same as we had before, the constant term. There's a mu here, there's a mu there, and there is a nu there. Oh my God. Terrible. So the first is just going to be A nu. That's the same exercise as we did before. That's the constant. But now, of course, we have this. So in this case here, we need to solve an integral of this sort, B nu x, integral 0 to infinity. No, not x. Oh my God. Mu x e to the minus x dx, where I've used x equals to t nu divided by mu. Okay. Did my on the fly variable substitute and pan out there? I think so. I hope so. You can check me and you tell me if I'm wrong. Yes, please. But you have the x, it's the t nu, right? Mu. Yeah, but you have this one. It cancels out there. But then you have this t nu. So t nu here, you have to have x times mu. So this is the mu that comes out from that. Yeah? Yeah. Now, this integral, you can solve. Or nowadays, you can, talk to your favorite AI assistant and get some assistant. It's not that. You solve it by integration by parts. Then it's actually straightforward. That's not what we're going to do today. It's not really the relevant part of this. The relevant part is that it comes out as unity, which is neat. Okay? So that the answer here is A nu plus B nu mu. Okay? Okay, that's interesting. What do we recognize by this? Well, it has the same form as the source function that we assumed. So we can write this as S nu tau nu in the c direction equals to mu. Okay, so what have we done now? I knew of mu equals 2 S nu tau nu surface mu. This is called the Eddington-Barbier approximation, and it's extremely useful in understanding some basic properties of radiative transfer. For example, we had a semi-infinite media now. We see to some sort of certain distance. We know there's going to be so opaque such that we don't see stuff from the most opaque layers. Now, what is it that we actually see? Well, we see the source function, but now that varies with optical depth, so with depth in the object. And where do we see it? Well, if we sit here now, yeah, and we're viewing this, and John, right? So mu equals to 1, we can call this one. Mu equals to 1, yeah? Then we see that if this is the surface now I'm going back to our plane parallel approximation. So this is the spherical version of it, right? We see the source, as it were, in this case for mu equal to 1, reflected at tau nu in the r direction here of 1. Right? So say that that's there. Then we see the source as it were at an optical depth of unity. And that's, of course, why we talk about this transition of optical depth unity as the sort of characteristic layer from which we see the light emerge. Right? Now, let's look at some position closer to the limb. Yeah? We're very, very far away here. Huh? So we see only parallel rays. So we're going to see this, and it's almost at mu 0. Yeah? Now then we see the source function at, in the radial direction, a higher position. Say we have mu equals to 0.1, then we only go down 0.1 in optical depth along this direction, so perhaps here. Yeah? Now, remember that this was defined along the fixed coordinate. But if you were to now say along the c coordinate or the r coordinate equivalently, then of course we know that the tau nu along the ray, yeah, is just going to be tau nu theta divided by mu. So if we take this in a plane parallel atmosphere, what it means is that if we're watching here, we're seeing down along the ray to tau nu equals to 1, right? And for a ray along the vertical in this case, that's equivalent to the tau nu c scale. Now, if we position ourselves here instead, and we're watching like this, we're still going to see tau nu along the ray unity, but that is going to be reached earlier in the atmosphere in terms of the vertical scale. This instead of here. and then we're seeing an upper layer. Okay? So it's along the ray that we're always seeing to optical depth unity, but the distance in the atmosphere, in the vertical direction, is less. And what does this mean? Well, we're going to see the source function reflected at those layers, roughly. So here, this is going to be the source function that we're seeing from this, but if we're positioned here, we're going to see it from this layer, which is deeper. Now, if the source function increases downwards in the atmosphere, which we have assumed, then of course this one is going to be higher than this one. So we're going to see more intensity at the center, mu equals to 1, than at the limb, mu equals to 0. This is going to be higher than this. And this is then the basic explanation for limb darkening. Okay? Now, let's see what time we have. All right, we do have some time. And like I said, such limb darkening can be important in various contexts. If you look online, you will see limb darkening of the sun. Very easy. I already mentioned, and we can just sketch this out. For example, if you have now a star emitting here, and you want to analyze a little planet going around this star when it comes in transit here, right? Then you look at the light curve, and you see that if there were no limb darkening of a star, then of course the light curve will be something like this, right? Yeah? But if it's limb darkening, then of course we're going to have more dips when it's in the center than when it's here. So that's one way where it's actually, if you want to have precise parameters, you need to account for limb darkening in that sense. Just as one astrophysical example of this. Now, you can also think of instances where this is opposite. That is, the source function decreases when we go inwards, that is, that it increases when we go outwards in the atmosphere, right? And that's, for example, the case in the solar corona, where the surrounding corona of the sun is very, very hot, for reasons which we will not discuss in this particular course. And there, the source function then can actually increase with height, and then it leads to the reverse phenomena, which we, of course, would call not limb darkening, but limb brightening, indeed. Supernova can also be exposed to such limb brightening effects. That's just two examples of that. And then the basic thing is that the source function then increases outwards. Yeah? We will come to, hopefully, get an intuitive way, feeling for when it is increasing inwards and outwards in various astrophysical systems. All right. Now, we also now see why we associate kind of like optical depth unity with how far down we see in the medium. One final thing here then that we're going to do. What about the flux? Okay, so we can look at this expression now and see what does this mean for the flux emerging from the object in the z direction. Well, we only have variations in the mu, so we can directly write down this integral here, where the phi angle, of course, has already come out. And then we had the I nu of 0 mu. And then we had mu, the mu. This was our expression for the flux. Go back to those lectures. if you do not remember it. Now we can just plug this in our Eddington-Barbier here. Where is it? Did I? It must be somewhere. I've sort of cancelled it. So the original expression was, of course, A nu plus B nu mu. Yeah, very pedagogic. So, and that was then our I nu of 0 mu. So we had nu plus the nu mu mu the mu. Okay, so what do we get out here? Well, the first thing to realize, this is only in the upward directions, yeah? So the flux integral then, of course, goes only from 0 to 1. Remember the discussions when we first introduced the flux, when we later introduced the effective temperature, the emitting surface where no incoming radiation. So then we get something like 2 pi. The first integral is mu from 0 to 1, so a nu is just going to come out, and that's just going to give you something like a half, right? A nu divided by 2. The second there is going to be the integral of mu squared 0 to 1. That just gives you a third. So it's this one there. We can just plug this out, and then we get, we take out the 2, then we get pi A nu plus B nu 2/3. So what is this? Well, this is pi. Then the source function at an optical depth C equals to 2/3. So we see that the intensity is always merging from along the ray an optical depth of unity, right? You take that, you put it over all angles, the average then becomes the flux. The weighted average becomes the flux, and that's then a reflection of the optical depth along the vertical axis of 2/3. And that's the simplest way we can think about why we often, so to say, define the surface of the star, the photosphere of the star or the object, the accretion disk or whatever it is, as the optical depth of 2/3. We will next week also look at a simple, very simple gray atmosphere model where this also comes out to be at the optical depth of 2/3 to further solidify that. But that was it for today, I think. Thanks. If you have questions,